Okay, welcome to the Reagents in Organic Synthesis live session. This is the first live session. So in this Google form, I found one question that is the regarding batch reduction. So I will make a presentation that might be more, I will explain more details there. So just a minute, we'll upload it. Okay, can you see the slides? Okay, so batch reduction. Okay, thank you. Okay, so we'll explain batch reduction in more details. So when benzene is treated with metallic sodium in liquid ammonia as a solvent in the presence of a proton source, as for example ethanol, methanol, or tert-butanol, the result is the net reduction of one of the double bonds of the benzene ring to give 1,4-cyclohexadiene. This reaction is known as the batch reduction, and here it has been shown, as you can see, the benzene goes to 1,4-cyclohexadiene in presence of sodium or lithium, liquid ammonia, and you need a proton source like ethanol, methanol, or tert-butanol. So alcohol as the proton source. So NH3 is the solvent, alcohol is the source of hydrogen, and this reactions are generally conducted at minus 80 degree to minus 33 degree centigrade. This is because the boiling point of ammonia is minus 33 centigrade. So your ammonia should be the liquid state. That's why this reaction temperature is lower, close to minus 78. Now the mechanism is that in presence of liquid ammonia, sodium goes to sodium plus, and one electron is liberated. That is called the solvated electron. That adds to the benzene ring, as you can see, and then after adding to the benzene ring, it forms a radical anion. So this stays in 1,4 fashion so that repulsion will be minimized. Okay, this one negative charge is formed and the radical, that is called the radical anion, they stay parallel to each other. Now this, in the second step, this anion takes the proton from the alcohol and it gets protonated. So this is called now pentadienyl radical. Now this radical will take another electron from the sodium that is solvated in the liquid ammonia and it goes to the negative charge. So radical goes to negative charge, it's called pentadienyl anion. So pentadienyl radical goes to pentadienyl anion, and this pentadienyl anion at the last step takes a proton again from the alcohol so that a neutral compound, that is the 1,4-cyclohexadiene, is formed. And the byproduct is sodium ethoxide. So alcohol is absolutely required for this step. NH3 is not acidic enough. So that's why you need a proton source like alcohol. Now we'll discuss substituent effects. Since the nucleophile here is essentially free electrons, the reaction is faster on aromatic rings with electron withdrawing substituents, as for example CO2H or H star, and slower on aromatic rings with electron donating substituents. This is understandable because electron withdrawing substituents will stabilize the negative charge and electron donating substituents will destabilize the negative charge. Now electron withdrawing substituents and donating substituents also give different products. Their pattern will be different, that we will see in a moment. So with electron withdrawing groups, you get protonation adjacent to the electron withdrawing group. So like this is benzoic acid, and if you put in Bart's condition, then you get this product, you can see, and the protonation happens at the carbon where the CO2H is connected. So this is the negative charge is formed there. Because the negative charge is stabilized by the electron withdrawing group. As you can see, the stabilization of the negative charge by the electron withdrawing group, the negative charge is delocalized to the CO2 group, and that's why it gets stabilized. And that's why this formed in the major product. Now, if you have an electron donating group like methoxy group, what will happen? Your negative charge will not be at the carbon where the methoxy group is connected. It will be at the ortho position. So your protonation will happen at the ortho position as well as the meta position, because always radical ion forms and they stay para to each other. So this is the major product form here, that your cyclohexanine, the double bond with connected with the methoxy group. Yes, as you can see, if the negative charge is there on the carbon where the methoxy group is there, then what will happen? There will be repulsion with the oxygen, and this minus or lone pair electron repulsion also is possible. Also, the OCH3 is pi donor, so that way it will destabilize. So only possibility is that the ortho position it can stay a radical, and the meta position a anion can be formed, and so that their distance will be maximum, so the repulsion will be less. That's why this will be the site of protonation. So thank you. I think I have explained you the batch reduction condition and the substitutance effects. If you have any other question, please ask me.
Sir, can you explain how the oxidative cleavage happen in case when we use MnO2 in dichloromethane?
Yes, MnO2.
Yes, sir. MnO2 in case of
Okay, that I did not have the slide because it did not fill in the Google form. But there will be like that. You have to cleave the sigma bond, and that manganese has 5 bonds, right? Manganese, right? MnO2. Okay, yes, MnO2 has 2 pi bonds. So two OH will attack to the manganese, and then the CC sigma bond will cleave. Okay. You can
Okay.
write to the TA. They will explain you. Okay.
Okay, sir.
Okay. If there is any other question, please ask. If there are no other question, then we can conclude. So thank you everyone and all the best for this course, Reagents in Organic Synthesis. Thank you.